Now the second part where these n equations or part of those n equations will come from is that each spline has continuous, has not continuous but has same slope at the interior data points, or some people what they call them is knots at the interior data points. Now what does this mean? So let's suppose I again draw this for the sake of completion. If I look at first two data points, and then I look at the next data points right here, next two data points. So this is x naught, y naught, this is x1, y1, and this is x2, y2. Now I know that this spline here which goes through those two data points, a1x squared plus b1x plus c1, and I know that the spline which goes through here is a2x squared plus b2x plus c2. But as we saw that in linear spline we have a drawback, and the drawback was that hey, each spline is not going through consecutive data points. The drawback was that the slope is not the same at the interior data points. So here what we can do is we can take this, since we have to generate n more equations, this seems to be a good way of circumventing, of answering that drawback of the linear spline, that the slopes are not the same at the interior data points. What I will do is I'll make the slope of this spline to be same as the slope of this line at this particular point. So what that means is that I'll take the derivative of a1x squared plus b1x plus c1, and I'll equate it to the derivative of the second spline, which is a2x squared plus b2x plus c2. And I'm going to equate them, but not at any point, but at x equal to x1, and this also should be at x equal to x1. So only at x equal to x1 I'm going to make the derivative of the first spline to be same as the derivative of the second spline. So what does that give me? That tells me that if I take the derivative, I get 2a1x plus b1 calculated at x equal to x1 is same as 2a2x plus b2 calculated at x equal to x1, and that gives me 2a1x1 plus b1 is equal to 2a2 x1 plus b2. And since a2 and b2 are unknowns, in order to be able to set up this equation, I'll have to take it to the left hand side. I'll get 2a1 x1 plus b1 minus 2a2 x1 minus b2 is equal to 0. So what you're finding out is that I'll be able to set up an equation which forces the first derivative to be the same whether I am using the first spline or the second spline at x equal to x1. So how many such equations will I get? What I will get is I have n plus 1 data points, but there are two data points which are on the exterior, like the first data point and the last data point. I don't have any spline before the first data point, no spline after the last data point. So that means that I have n minus 1 interior points. And those are the only places where I can set up this equation of this particular form. So what I will get is I'll get n minus 1 equations like that. So now if I was going to write down these n minus 1 equations which I'm going to get the interior data points for a general point, let's suppose same thing as we did previously. So let's suppose this is x of I comma y of I. This will be x of I plus 1, y of I plus 1. And then I'll have here will be x of I minus 1 comma y of I minus 1. So this particular spline here will be equal to a of I x squared plus b of I x plus c of I, and this spline here will be a of I plus 1 x squared plus b of I plus 1 x plus c of I plus 1. And I want the slope to be the same at this particular data point, which implies that 2a of I x plus b of I calculated x equal to x of I will be same as 2a of I plus 1 x plus b sub I plus 1. And the way why we have 2 sub a, this kind of expression is because we're taking the derivative of this, and that's this, and the derivative of this spline here is 2 sub a plus 1 x at b sub I plus 1, and that's at x equal to x of I. So then what that means that 2 sub a I x I plus b sub I will be equal to 2 a sub I plus 1 x of I plus b sub I plus 1. And how many such equations will I have? I'll have n minus 1 equations. So I will take the value of 1 to n minus 1. So it will take n minus 1 values of I will be taken by this particular equation here. Of course, I have moved all this to the left hand side to set up those n minus 1 equations. So that's what we're talking about, is n minus 1 interior data points. So we'll get n minus 1 equations. So what that implies is that we already got 2n equations from saying that each spline is going through consecutive data points, and then that the first slope or the first derivative is continuous at the interior data points. So we had 2n equations coming from that each spline is going through 2 consecutive data points. We had n minus 1 equations coming from the fact that the slopes are same at the interior data points. So we're going to end up with 3n minus 1 equations. So what that implies is that we have to find one more equation. One more equation is needed, because if I don't have one more equation, I don't have 3n equation, 3n unknowns. So what I will do is I will look at the 3nth equation will be as follows. I might say, hey, let a1 be equal to 0. And that becomes my last equation. So if a sub 1 is equal to 0, that's basically assuming that the first spline is a linear spline as opposed to a quadratic spline. And some people will also may take a sub n equal to 0 based on whether the distance between x0 and x1 is smaller than the distance between x of n minus 1 and x of n. That's something which you can think about. So, but for my purposes, I'm going to take a sub 1 equal to 0 to set up the 3n equations, 3nth equations. So I have 3n equations, 3n unknowns. So once I have 3n equations, 3n unknowns, I solve for all the a sub i's and b sub i's and the c sub i's, and then I can use those to be able to interpolate at any point which I want to. And we'll do an example in the next segment to be able to illustrate that. And that's the end of this segment.